Hello everyone. I hope that all of you are enjoying good health. Welcome to another lecture of robotics and automation. And this lecture is about motion planning. In the previous lecture, we studied about forward and inverse kinematics, in which you have given some joint positions, and then you have to calculate the position of your end effector, or the other way around. But for if you see in the real world, the task of the robot is to move in the environment actually. Okay, for example, let's take a pick and place operation by a robotic manipulator. So the robot has to actually move from one place to another place, and this process requires motion planning. So what is motion planning? Here it's given. Motion planning is the problem of finding a robot motion from start state to goal state that avoids obstacles in the environment and satisfies other constraints such as joint limits or torque limits. So let us consider a 2D environment. Let me draw it. Okay, so here is our 2D world example, and here you can see this. We have our 2R planar robotic arm here, and then we have a start position and a goal position, and also two obstacles, obstacle 1 and obstacle 2. So normally the task is to pick any object from start position, and then using this gripper you have to pick the object from here, and then avoiding these obstacles, the end effector the gripper should move in the world and then reach the goal position, avoiding collision with the obstacle, and then finally reach the goal position and then place the object there. So we have something like these kind of tasks, and for these type of tasks we need a kind of path, a trajectory that avoids collision with the obstacles. So when we are talking about the collision, the collision can be the collision between the end effector and the obstacle, or even the collision between the links or joints of the robotic arm with the obstacle. So we need to design a path or a trajectory that avoid these collision with the obstacle, and it takes the end effector of the robot to the goal position. And the second thing this path or this trajectory must satisfy is that it must satisfy the joint limits and torque limits, because this robotic arm here, with each joint, let's say we have a motor, a DC motor, that has its own limits, and also the link of this robotic arm, it can rotate within a certain angle. Sometimes it's 180 degrees, sometimes it's more than 180 degree or less than 180 degree. So these joints here, they have their own limits. Okay, position limits, angular position limits, and also the torque limits. So we have to consider also these two things while we are motion planning for our to our planar robotic arm. So this entire process, we call it motion planning, and a key concept in the motion planning is a configuration space, or C space for short. Every point in the C space corresponds to a unique configuration Q of the robot, and every configuration of the robot can be represented as point in C space. So let's say we have again a 2R planar robotic arm here, and it has 2 joints and 2 links here and an end effector. So the specification of this joint 1, which is theta 1 here, and then an angle theta 2, this is the configuration of this robot. Okay, and let's say this configuration is, we have C1, we call it configuration C1, when theta 1 and theta 2 have specific values. For these specific values, this configuration C1 corresponds to a point in your C space. This is a C space here, this X and Y axis, which specify the values of all values of theta 1 and theta 2, and in this configuration space, which we call it C space, this C1 corresponds to a specific point, and let's say we call it here we have C1, and this C1 corresponds to a specific point. Let's we call it here, this point here. Okay, for this configuration there is a single point in your C space which represents this configuration C1. And similarly, if you see again the same robot, to our planar robot, but this time it has a different configuration. The joint values theta 1 and theta 2, they are different. Okay, so this time it has a different kind of configuration, and let's say this configuration we call C2, and this C2 will again be represented by a different point in your C space, and let's say this C2 is represented by this point. So whatever the configuration is, it can be represented by a point in your C space, or the other way around is every configuration of every point in a C space correspond to a unique configuration Q of the robot, and vice versa. The configuration of a robot arm with n joints can be represented as a list of n joint positions. Okay, so in this case we have only 2 joints which can be represented by theta 1 and theta 2. Okay, the angular position of 2 joints is the configuration of this robotic arm. But if you have n joints, n number of joints, of course things will get more complex, and so the values of all the joints of the robot, it will be the configuration of the robotic arm. The free space The free C space, which is also known as the C free, consists of configuration where the robot neither penetrates an obstacle or nor violates a joint limit. So in a C space like here, so this is two C space with two joints, and we name it theta 1 and theta 2. So this theta 1 and theta 2, they are the joint angles, and then this is our C space. We can write here the whole space is called the C space, and this one here we call it obstacle space. This is obstacle, and the space occupied by this, we can call it obstacle space, and the other region that is not occupied by any kind of obstacle in the C space, we can call this region as C free, and the whole area region we say this as C space. So yeah, so during motion planning or path planning, what we need that our robot should stay in this C free while moving, and it should avoid the obstacles or obstacle space. Okay, so yeah, so let's now slowly move forward, and we move toward some more details about motion planning. And the first thing we discuss is types of motion planning problems, because motion planning can have different types. The first thing you should be clear about is the difference between path planning and motion planning. Okay, the path planning problem is a sub-problem of general motion planning problem. So motion planning is a broad field, but path planning is you can say subfield of this motion planning. So in a path planning is purely geometric problem of finding a collision-free path from start configuration to goal configuration without concern for dynamics, the duration of motion, or constraints on the motion or control inputs. So what path planning is just finding a collision-free path from start position to your goal position. Okay, and in path planning we are not concerned about the dynamics of the robot. Like in the previous lecture, we talked about the kinematics of the robot, forward and inverse kinematics, and same is we can also drive the equation of dynamics, in which we have to deal with the forces and torques acting on the robot using Newton's method. But we haven't covered in this course dynamics, because the objective of this course is different, and the dynamics portion is not within the scope of this course. So yeah, so the motion planning actually involves more than just path planning. It involves dynamics, and then you have to satisfy some torques and forces. And also the important thing is you talk about in the motion planning, we talk about the control inputs to the robot. Okay, so we talk about, okay, which joint will should exert how many force. Okay, so yeah, so in motion planning we talk about the control inputs, dynamics, but in path planning we just focus on the path which is not in collision with the obstacles, and it leads from start to goal position. It is assumed that the path returned by the path planner can be time scaled to create feasible trajectory. So once you have a path from start to goal location, then later it can be time scaled to get a trajectory. So this is trajectory generation task, and we shall study a little bit about it at the end of this lecture. Okay. Control inputs. If there are fewer control inputs m than the degrees of freedom n, then the robot is incapable of following many paths. So it is about the controllable degrees of freedom and actual degrees of freedom. Okay, if there are fewer control inputs, which we can represent by m, then the degrees of freedom of the robot can be represented by n. Then the robot is incapable of following many paths, even if they are collision free. For example, a car has 3 degrees of freedom, which is its XY motion and the rotation in the plane. But only 2 degrees of freedom are controllable, which is the forward-backward motion and the steering. You can control the steering angle. So that's why the car cannot slide directly into sideways, okay, in a parking space. So whenever you if you have driven a car, you can understand this quite easily. So whenever you have to park a car in a parking lane, so because it cannot move sideways directly, instead you have to kind of rotate it and change its position and orientations to achieve a specific position and orientation. So that's why you can say that it has less controllable degrees of freedom, or less control inputs as compared to degrees of freedom. So this is a control, again a motion planning control problem, and for that you need only path planning is not enough. Actually, you need motion planning, in which you have to deal with the limited control inputs. Okay, another type of motion planning problem is, we can categorize the problem as online versus offline. This is offline here. A motion planning problem requiring an immediate result, perhaps because obstacles appear, disappear, or move unpredictably call for the fast online planner. So online planning, we have to use it where in real-time scenarios, okay, where you have to react immediately. Obstacle appear, for example, if your environment is dynamic, where the obstacle change its position and suddenly new obstacle can appear. So in this case you have to use online motion planning, because you need fast reaction, and for that you need your motion planner should be able to react faster and plan new path. But if your environment is static, then a slower offline planner may be enough, okay, because offline planning is something where the obstacles are not moving or not changing, and you know that exactly where the obstacles are related and how many obstacles are in the environment, and then according to this static environment you do path planning, you generate a path, and then the robot just follows this path. So you don't need very fast real-time or online planning. So this is again a type of a motion planning problem. While designing a motion planner, you need to consider this also. You need to take into account. Another type of motion planning problem is the optimal versus satisfying problems. In addition to reaching the goal state, we might want to motion plan to minimize, okay, or maximize something. And in a specific case, we can say to minimize some kind of cost, because up to till now we were talking only about the finding a collision-free path from start to target position, but motion planning problem can also be optimal problems, where you have to find the shortest path, okay, shortest means that will be the shortest length path, or you can say lengthwise, or you have to minimize some other criteria. For example, you have to minimize the energy consumption, or you have to minimize the fuel consumption. So this is a category of actually optimal motion planning. Okay, another category of motion planning is exact versus approximate motion planning. We may be satisfied with the final state x of t that is sufficiently close to the goal. So in exact motion planning, what we are looking for, we are looking for actually the exact final state. Okay, we want that our motion planner should find the exact solution to the problem, okay, but sometimes finding the exact solution, it requires so much energy and computational power that our other option is to go for approximate solution, which actually does not guarantee you the 100% accurate result, but your results will be sufficiently close to the goal or the final state. Okay, then we have motion planning problems in which there are obstacles or some are without obstacles. The motion planning problem can be challenging even in the absence of obstacles, particularly if the optimality is desired. Yes, that's if you are looking for optimal solution, if you're looking for minimizing or maximizing some cost function, then even without obstacles, motion planning is a hard problem, a difficult problem. So yeah, so our this section is completed, in which we have studied different types of motion planning problems. And so most of time, the basic thing we can start with is just with path planning. This is the simplest one, in which we just have to find a collision free path from start to target position. We don't need to consider about the torques, about the control inputs, or here we also can select the easiest one, which is offline path planning, in which we assume that the environment is static and the obstacles are not moving, and then we can ignore optimality. Okay, at the start we say that okay, only the feasible solution is enough for us. We don't need to minimize or maximize some cost function. And yeah, but we can also, if we drop the optimality, we can consider some obstacles in the environment. But again, if you want to make your problem more accurate and close to the real world scenarios, then you have to make it like more complex. Okay, you have to choose the exact nature of your solution. You have to include obstacles. You have to you need to find optimal solution, and it should also be online, because the real world is actually online. Okay, in real world obstacles are moving, and also control inputs are also sometimes less than the degrees of freedom of the robot. So yeah, let's move now to properties of motion planners. So the first property of the motion planners is that, are they multiple query or are they single query planning problems? If the robot is being asked to solve a number of motion planning problems in an unchanging environment, it may be worth spending the time building a data structure that accurately represents C-free. This data structure can be searched to solve multiple planning queries efficiently. Single query planners solve each new problem from scratch. Okay, so single query means that only one time path planning or motion planning is desired. For example, if a robot wants to move from one position to another only one time, then this is a single query problem. Okay, so in these types of problems, you just make you try to solve this problem, keeping in mind that you will solve this problem only one time, single time. Okay, but another scenario can be you have to use multiple times you have to do multiple path plannings. For example, at the beginning the robot moves from one position to another position, and then the robot has to move again to some other goal location, and you have to use these multiple times the motion planning. Okay, so in this case you have to actually solve this problem, keeping in mind that you have to build your data structure in your to represent your C free in such a way that you don't need to repeat steps again and again. Instead, you have to build your data structure such a way that it's reusable and it can be used for multiple times planning or motion planning a path. So that's the difference between single query and multiple query motion planners. Then we have another property of the motion planner, which is anytime planner, anytime planning. An anytime planner is one that continues to look for better solutions after a first solution is found. The planner can be stopped at any time. For example, when a specified time limit has passed and the best solution returned. So what happens is that initially anytime planners, they as the name suggests, it can be stopped anytime. For example, you want to plan a path from in a configuration space, and you started planning, you started to run your algorithm of path planning, and then you just stopped it. And even if you stop it, it will give you some kind of solution. Okay, and if you keep it, let it run for enough time, it will give you even the best solution. But if you stop it earlier, it will still give you some kind of solution. It will not be the best solution, but still the solution will be there. So this property we call anytime motion planners. And not every algorithm or not every motion planner is anytime. Some of them, they don't work actually. If you stop them earlier, they will not work. They will not give you any solution. But there are some planners that are anytime planners. Okay. Another property of motion planning is completeness. So completeness is related to finding actually the solution if it exists. It's actually a guaranteeing that your solution will be found. So a motion planner is said to be complete if it is guaranteed to find a solution in finite time if one exists, and to report failure if there is no feasible motion plan. So this is completeness. If your motion planner guarantees that it will find a solution in a finite amount of time, in case if the solution actually exists, okay, then it will call a complete motion planner. And in case if the solution doesn't exist, then it should report also that the solution is not feasible actually. So this type of motion planner, we call it complete motion planner. Now the thing is, sometimes it happens that your configuration space, it is filled with too many obstacles that there is no path possible. The robot cannot actually move. There is no path without collision with the obstacles. So in this case, if you use a complete motion planner, it will say that okay, no feasible solution exists, no feasible path exists. But if your motion planner is not complete, it will fail to actually find a path, or it will not recognize if the path doesn't exist actually. Okay, a weaker concept is a resolution completeness. A planner is resolution complete if it is guaranteed to find a solution if one exists at the resolution of a discretized representation of the problem, such as the resolution of a grid representation of C-free. So this is, we are talking about now the resolution completeness. So normally what we do, we sometimes this property is related to the resolution of the problem you're going to solve. So normally what we do, we try to, for the path planning, we divide our C space into a type of grid cells. We divide them into cells, and then we try to find a path from start position to your goal position. And the resolution of this grid, resolution means number of these cells, these grids. It's also very important in your finding a solution. Okay, if it's these, there are two less cells, then your motion planner might not be able to find a solution. So it will not guarantee completeness. But if the resolution of this grid is enough, then your motion planner may guarantee completeness, may guarantee to find a solution, a path. So these types of problem, we call them, this property, we call it resolution completeness, because the guarantee to find a solution is dependent upon the resolution of the grid. Okay, another type of completeness is probabilistic completeness. A planner is probabilistically complete if the probability of finding a solution, if one exists, tends to 1 as planning time goes to infinity. So probabilistic complete planners, they will guarantee to find a solution, okay, if you allow them to run for infinite amount of time. Actually, they don't go for, in practically they don't run for infinite amount of time, but the probability of finding a solution, actually they will give you 100% results if you let them run for enough amount of time. They will give you the solution. And some they may also give solution earlier, but it's not guaranteed. Okay, so see the difference. The difference is that the probabilistic motion planners, they will find a solution, okay, but the guarantee that they will find a solution 100% is if you let them run for infinite of time. But actually in the real scenarios, they may find solutions earlier, like in a couple of seconds, but there is no guarantee. Again, they may find, but they may not also. So this depends upon the probability. Another property of motion planner is their computational complexity. The computational complexity refers to characterization of the amount of time the planner takes to run, or the amount of memory it requires. So yeah, because we have limited resources, so the amount of time and also the memory required to solve a problem. Okay, this we call it computational complexity. These are measured in terms of the description of the planning problem, such as the dimension of the C-space or the number of vertices in the representation of the robot and obstacles. So this complexity is dependent upon the how we describe our planning problem. We can make it like much more simpler, and also we can add more details to make it more complex. So its complexity depends upon dimension of the C-space we are going to choose. Of course, if we have more joints, if we have more dimensions of the C-space, if we have more degrees of freedom, then it will going to be complex. Or the number of vertices in the representation of the robot and obstacles. If we just consider the obstacles as just circles, and also we consider the robot as a point, then things will be easier. Your problem will be less complex, or computationally it will have it requires less computational effort. But if you describe your robot like more with a complex shape, and also you describe the obstacles with more vertices, with more like complex shapes, then your problem will become more computationally complex. For example, the time for a planner to run may be exponential in n, the dimension of the C-space. Okay, so this is one of the examples that how the computational complexity increases with the increase in the dimensions of your C-space. Up to till now, if you remember, we were talking about a two-dimensional C-space in which on the x-axis we had θ1, and then on the y-axis we had θ2, and this was our C-space here. And so if we increase the dimensions n of the C-space, let's say now this time another C-space we have this is a 3D C-space which we have θ1, θ2 and θ3, three dimensions, then the computational complexity of your motion planner will increase exponentially with the increase in the number of dimension of your C-space. Okay, so yeah, the computational complexity may be expressed in terms of average case or worst case. So when you run a motion planner algorithm for motion planning, so you have to select that either you want to find the computational complexity for average case or the best case or the worst case scenarios, because they will be different depending upon the number of obstacles in the environment and the position of your goal and start locations. So each scenario will be different. So at the end you can either take an average of all the scenarios and you can say this is your average case computational complexity. Okay, or you can also talk about the worst case in which your environment is completely not completely, it has most obstacles and it is very difficult for a motion planner to find a path. And so this will be, in this case, the time it takes to find the solution or find a path, and the memory required by the algorithm, motion planning algorithm, it will be the computation complexity. Some planning problems lend themselves easily to computational complexity analysis, while others do not. So for some problems it's easily to find out what will be its complexity, how much time it will take, and how much memory it will take to find the solution. But for others it's really difficult. You cannot really predict that. So these were some properties of the motion planners, and now we quickly move to the motion planning methods. So there are many motion planning methods actually. In this course we shall not go in detail of all of them, but if you are interested, then you have to study by yourself. Okay, you can refer to the book. It's called Modern Robotics, and chapter number is 10. So here you will find more details about the motion planning methods. Or you can also watch my videos available on the YouTube. So let's begin with the motion planning methods. Actually, there is no single planner applicable to all motion planning problems. So you remember we discussed in the previous slides types of different motion planning problems. All of these: online, optimal, exact, or depending upon the control inputs. So not a single method available. They can be applicable for all motion planning problems. Every motion planning method we have available, it has its own advantages and disadvantages, and none of them can be applied is like a perfect one and can be applied for every motion planning problem. Okay, the first method for motion planning we're going to discuss is the complete method. These methods focus on exact representations of the geometry or topology of C3, ensuring completeness. So how it works is that this is, let's say, our C space, and we have two obstacles here. Let's name them. This is obstacle 1, and here we have obstacle 2. So what happens is that there is a method, we call it visibility graph. So in this visibility graph method, what we do, we try to connect the vertices of the obstacles that are visible to each other. For example, this obstacle 1 has 3 vertices, 1, 2, 3, and this also obstacle 2 has 4 vertices. So if you see that which vertices are visible to each other, so from here obstacle 1, this vertex is visible to this vertex here, and this is also visible to this vertex, but it's not visible to this vertex here. Okay, for example, if a person is standing here, it can see this vertex, and also this vertex here, but it cannot see this behind one. And similarly, if you are standing here, you will see this vertex. If you're standing here, you will see this vertex and this vertex. You can just call it corner. If you're standing here, you will again see this vertex, and yeah, but you will not see the behind one here. Okay, so how the purpose of our motion planning is to find a collision-free path from start to your goal position. So you have to define here your goal location. Where is this goal location? So let's say this we have this point is our starting point, and this is our goal location here. Now so these complete methods, they use the exact representation of your C-free. So you see that it shows you where the geometry of the free space between these obstacles. And so what it does, it just connect the start point with the nearest visible vertex. So the nearest visible vertex is this one. This one is not the vertex included in the visibility graph, because the graph only consists of these vertices here. This one here, this one here, this one here, this one here, and here. So how many vertices we have? 1, 2, 3, 4, 5. 5 are in this visibility graph. They're visible to each other. And this here and here, they are not visible, so they're not connected. So these 5 vertices are connected by these edges with each other. And then what you need to do, you just need to connect it with the nearest one. Okay. And also you have to connect the goal with the nearest vertex, visible vertex. So now your robot can reach from your start position to your goal position just by following this path. It will start from here. It will go from here to here, and then from here it will just follow the shortest path. It will go from here to here, then from this vertex to this here, and then from here to here, and then finally it reaches the goal point. So this is how we do path planning using the complete methods, and they guarantee to find the solution if it exists. So if there is a path, these methods will definitely, for sure, find your path. For all but simple or low degree freedom problems, these representations are mathematically or computationally prohibitive to drive. So these kinds of methods, the complete methods, they are good for the low degrees of freedom problems, okay, where you have less dimensions in your C space, and also there are less obstacles in the environment. You see that the more edges an obstacle has, the more this visibility graph will become complex, and the more number of obstacles you have in the environment, the more computationally expensive this method will become. So it's best suited for the low degree of freedom problems, where you have like a planar 2 degree of freedom robot, or a simple mobile robot. but for the higher degree of freedom problems, this method is very computationally expensive. Okay, so this was a first method for motion planning, and now let's go for second method. So the second method is a grid method for motion planning. This is I would say the most commonly used method. And how it works is that these methods discretize C-free into a grid and search the grid for a motion from Q start to a grid point in the goal region. Modifications of the approach may discretize a state space or control space, or they may use multi-scale grids to define the representation of C-free near obstacles. So what generally this method does is it divides your space, configuration space, into a grid. So how it does that? It just creates a grid like this, and in this grid you have some obstacles. So let's say if you have obstacles somewhere like this, so this whole grid, because of this obstacle, this whole grid will become obstacle. Okay, and yeah, so how it works is that for example, this is your start point here, this is your start grid, and this is your, let's say, goal grid here. So what you want to do, you want to find a collision free path from start grid to goal grid. So there are many algorithms available, for example breadth first search algorithm, and so this algorithm is used to find a collision free path from start point to goal point. Let's say this is obstacle also, and let's make some more obstacles. Let's say this is also an obstacle we have. So let's say we have 1, 2 and one more obstacle here. So we have 3 obstacles here, and the other grid cells, they are the free. So here your robot can move, and also your motion planner can find the path. So we can use breadth first search algorithm, we can use Dijkstra's algorithm, we can use A-star algorithm, to find the path, and the path will look like something like this. It works like moving from start and grid by grid in discretized step by step. It will try to reach your goal position. So this will be your collision free path from start to goal location. And exactly how this works, the breadth first search, A-star algorithm, we shall not go in detail of all of these methods because it's not in the scope of this course, but we shall briefly discuss one of the methods, that how this breadth first search work. But generally speaking, that these methods are relatively easy to implement and can return optimal solutions. So this is their advantages. They are easy to implement. If you as compared to complete method where you have to connect the obstacles, the vertices of obstacles, These methods are easy. Just you have to make a grid, and then you have to define which blocks, which grid cells are obstacles and which are the free cells, and then use a suitable motion planner or path planner to find a collision free path. And they can also be used to find optimal solutions. But for a fixed resolution, the memory required to store the grid and the time to search it grows exponentially with the number of dimensions of the space. So this is one of the problems with these grid methods, is that as the number of your dimensions of your C space when number of dimensions of your C space increases, okay, for this is a 2D grid, and if this becomes a 3D grid, then the computational complexity, the time and memory required to find this path or a solution will increase exponentially. That's a problem with these kinds of methods. This limits the approach to low dimensional problems. So this is one of their, again, the drawback is that, like the complete methods, the grid methods, they are limited to low dimensional problems where you have a few dimensions, let's say 2D or maybe 3D, and the grid size is also small. So these methods are suitable there. So later we discuss one of the motion planning methods for grid, but now you have a general idea how the grid methods work. Let's move to our next method, which is a sampling method for motion planning. So sampling methods, how they work is that they take random samples of your C space. So let's say this is your C space here, two-dimensional C space, and let's add some obstacles inside it. So how they work is that these kinds of methods, they take random samples of your free space, C free. So this is let's say this is your C space, two-dimensional 2D C space, okay. And so what these method does, why they call sampling methods, because they use mostly random samples of your C free. A generic sampling method relies on random or deterministic function to choose a sample from C space or state space. So the sampling can also be deterministic, but mostly we use random sampling. A function to evaluate whether the sample is in C free. So what we does, we randomly, let's say we use random sampling, we randomly take a sample from this C free. So this is, here we have obstacle space, and we are not interested in this one because our path cannot enter in this space, the obstacle space. Our path, our solution only relies dependent on this free space, so the robot can move only in this space. So we are only interested in here. So the first step, we take a random sample anywhere, random sample, take a sample, let's say I take a sample here, this is I call sample 1, and so now I will take a I have to evaluate whether this sample is in C free or is it in the obstacle. If let's say this sample is inside your obstacle, then it will not be considered, it's not important, we just discard it. If it's in C free, then this sample is now, it will be used further. In the further step, what will happen? A function to determine the closest previous free space sample. So we look for the previous samples that we have already taken from the C free. Till now we have only one, but let's say we take another sample that is here as 2, but this sample is inside your obstacle, so this is not important. So we take one more sample, and this sample, let's say, is here, it comes out here. This is our sample 3, and we now see that we need a function to relate this new sample with the previous sample. Okay, so here we need this function to relate these two samples. A local planner to try to connect to or move forward the new sample from the previous sample. So now we need to connect these two samples, and what we do, we try to see that either if we try to connect these two samples, then either they will be in collision with the obstacle or not. So this path that connects, this edge that connects these two samples, is this edge is in collision with obstacle or not? So that's what we are looking for. And yeah, so by taking random samples, let's say we take one more sample as 4. So this was, I forgot to mention, this was our starting point as 0, and from here we take sample 1, we connect it. Sample 2 was in obstacle, so we delete it. Sample 3 was in C free, we take it, and then sample 4. Okay, and let's say this is our goal location. And similarly, after some samples, we stop the sampling and we just try to connect the goal with your nearest sample. Or if your S5 is on your goal, then the algorithm will stop. And otherwise, if your samples are finished, you finish sampling after some time, then you just connect your goal with the last sample, nearest sample. And so now you see that if you connect all of these samples, this will give you the shortest path from start to your goal location. This process builds up a graph or a tree representing feasible motions of the robot. So you see that in this process of connecting the random points, we're building a graph. Actually, it's a tree. For example, if you take more samples, let's say if I take sample S5 here, this sample will be connected to S1 because this is the nearest one here. S5 is nearest to S1. And let's say if I take one more sample here randomly anywhere, so let's say this is the sample S6. Sample S6 is nearest to sample S3, so we connect it. So you see that it's making a graph here. It's a tree graph. Okay, so what is a graph? Graph is a combination of nodes, points that are connected with edges to each other. So yeah, we are making graph here, and so in this graph we try to just search for some feasible path like this. So in this case we move from our start position, we go to S1, next sample, from here we go to S3, then go to S4, and then finally we reach the goal location. Sampling methods are easy to implement, tend to be probabilistically complete, and can even solve higher degrees of freedom motion planning problems. yeah, they have pretty strong advantages. Okay, the first one is they are easy to implement. You don't need grids, you don't need visibility graphs, and they are probabilistically complete. We already studied that what is probabilistical completeness, and can even solve higher degree freedom problems. Yeah, in the previous two methods that we studied, the visibility, the complete methods and the grid methods, they were unable to solve they were like mostly used to solve for low dimensional problems where the your C space was very simple, and but they were not feasible for high dimensional C space problems. But these methods, the sampling based methods, they are suitable for higher dimensional problems. The solutions tend to be satisficing, not optimal, and it can be difficult to characterize the computational complexity. So now it has also some disadvantages, and one of the biggest disadvantages of these methods is that they tend to be not optimal. Not all of them. There are some who are they can give near optimal solutions, but generally because of their random nature, they tend to be not optimal. And also to find their computational complexity, it's also difficult because of their random nature. So this was our third motion planning method, and let's go for the fourth one, which is the virtual potential fields. So virtual potential fields create forces on the robot that pull it toward the goal and push it from the obstacles. So these types of methods, they try to model your C space like that. Your robot is attracted toward the goal and it is being pushed away from the obstacles, like similar charges push each other and the opposite charges attract each other. The approach is relatively easy to implement even for higher degrees of freedom systems, and fast to evaluate, often allowing online implementation. Yeah, this is one of the strongest points here. So these methods, they can be used for online. The previous methods that we were discussing, they might be used online but not easily. They are mostly used offline, but not always. There are some variations where you can use also online, but mostly they are used offline planning. But this virtual field method, they can be used online, so they're fast. The drawback is local minima in the potential function. The robot may get stuck in configurations where the attractive or repulsive forces cancel, but the robot is not at the goal stage. So that's a problem, one of the problems when you model your environment like this. So that's one of the problem here. You say that, okay, you have here obstacles, and so let's say here you have the goal location. This is your goal and this is your start point here, and you represent this C space like this, so that your robot, it is always attracted toward the goal, and it's being repelled by the obstacles. So you model it like a force, attractive and repulsive forces acting upon the robot. So it will start moving toward the goal, and here it will experience the repulsive forces from the obstacle that will push away a little bit. So the robot will not move toward the goal. So these green forces are repulsive forces, and the red one is the attractive forces. So both the combined effect of these repulsive and attractive forces, it will move your robot from start to your goal location, avoiding the obstacles. So yeah, so here we have two I would say C spaces. This is one for the real world, and this is the C space. And so the point here we are trying to make is that how we can represent the obstacles in the C space. The representation of obstacles in C space may be different than the original shape of obstacles in environment. So yeah, so the point we are here trying to make is that this is, let's say, your environment, real world. We call it real world environment, and this one here we have C space. So we are taking an example of of a robot that is a circular robot we have here. Let's say here we have a circular robot, and let's also represent some obstacles. Let's say here we have obstacle, and this obstacle looks like this. So this is a real world scenario, a real world environment in which you have a robot here. This is mobile robot, so it's a robot with wheels. It can move around in this environment. And here we have obstacle. So how many configurations or how many degrees of freedom this robot can have? So this mobile robot can have X, Y, and theta. So it has 3 degrees of freedom. So it can move along x-axis, it can move along y-axis, and also it can rotate about z-axis, which is theta. So this I'm talking about the real world here. Okay, so now we have to represent this thing in the to simplify the calculation. Let's say this is only 2 degrees of freedom. This mobile robot has only 2 degrees of freedom, so we can take it as a point, this circular robot as a point here, and so it can move along XY axis without rotating. Okay, so how it will look like this. So if you now want to represent this thing here, so it will look like something like this. So I have already drawn it. So when your robot will be moving in this environment, so in case of C space, when the robot will reach actually near this obstacle, so the center point of robot cannot actually reach near the obstacle more than half of the diameter. Okay, so this center point of the robot will always be one radius away from this obstacle. So it means that the space between the center of your robot and the obstacle, this distance will always be equal to the radius of the robot. Okay, so that's why we can consider now this whole thing connecting the center point. So this whole region we can consider it as obstacle. Okay, so you can also say that in C space now the obstacle has been changed, it's become bigger, because how much bigger? Equal to the radius of the robot in every direction. Okay, so that's what I'm trying to say here. The representation of obstacle in C space may be different than the original shape of the obstacles in the environment. So why they are different? Because it depends upon also the degrees of freedom of the robot, or you can say the size of the robot. If the robot size is bigger, then here your obstacle is also become bigger. So now your final obstacle will be the area within this red line. Okay, this will be your final obstacle. And so you see that your obstacle in C space, this is bigger than the obstacle in your original environment. So we shall do motion planning or path planning with respect to this our new obstacle. Okay, so we can write now, let's say here is a start position of the robot and here is the goal location. So now your robot moves something like this, avoiding the obstacles. Okay, but if you don't do that, if you don't do this, then there is a chance that this path will move near the obstacle. Okay, and because while drawing the path we were actually considering the robot as a point, but actually the robot is not a point, it has some radius, it has some size. So when it passes near the obstacle, it may collide with the obstacle. Okay, so that's why, to avoid this problem, we already inflate the obstacle so that to compensate the size of the obstacle. to compensate the size of the robot. I hope that this concept is clear. Okay, now let's move forward and let's see how we can do the path planning of a 2R planar arm. Okay, this I already have drawn it. So consider a 2R planar robot given in this leftmost side of the figure, and here you can see that it has two links and two joints with angle θ1 and θ2. So when this robotic arm is in the real world, so it must face some obstacles. So here in the middle figure we have this two obstacles A and B, and then we have the start position of our robotic arm. This is the, you can say this point is a start point, and then so now what we want, that we want to reach our robot at the goal location. So this is a goal location. So this I have shown this location within other configuration of the same robotic arm. So when your robot will reach at the goal location, it may have this kind of configuration, but it's not a must. So the important is to reach from start. The end effector of this robot should reach from start location and then moving slowly toward the goal location here. So this is our this will be the process, but the important thing is that there should be no collision between the end effector and the obstacle, and also there should be no collision between the links of the robot and the obstacle. So as you can clearly see that here, while going from start to goal, only the obstacle A will be important, and B is not really important because it's not going to encounter during the process. So here what I have shown here in this figure, this is actually a workspace of you can call it workspace of the robot, and now our goal is for path planning or motion planning of this robot. So if you just look at this figure, how you think that the robot should behave, how it can, the methods that we have previously studied, like grid methods, graph methods, if we apply them here and we say that okay, this is the end effector of the robot, and if we just only consider the end effector, okay, for path planning, and let's say we apply here a grid method for path planning, we are just considering the end effector. So it will give you path something like maybe this here, like this. But the problem with this kind of only considering the end effector for path planning is that if there are more obstacles within here, let's say somewhere here or here, when there are more obstacles, then this cannot be included during the motion planning or path planning process. So to avoid this problem, what we do, we convert our workspace into a C space, configuration space, in which you have θ1 which starts from 0 to 2 pi. So this robot can rotate like 360 degrees, and similarly the θ2 angle also, it starts from 0 and it goes to 2 pi. It means the second link of the robot, this one and this one here, it can also rotate 360 degrees. So now the process, the important thing is that our C space is just the joint angles, all possible values of the joint angles. So now you have to see that when how to map the obstacles from your workspace to your C space. Okay, let's take an example of obstacle B first. So how you gonna map obstacle B, which is in the workspace, to your C space? So consider this link L1. Okay, so this link can move from here to here independently without collision with the obstacle. Okay, and then at an angle, somewhere angle that is you can say more than 90 degrees. So there is a chance that there will be collision with the link 1 will be in collision with the obstacle B. So that's what shown here. So from 0 to somewhere 90 and 90 degree or more than 90 degree, there is no collision with obstacle B, and after that, when the angle is more than 90 degree and less than 270 degree, so there is a collision with obstacle B. So here I have drawn obstacle here, the B obstacle, that's why. And for link 2, it can rotate freely without collision with obstacle. Just imagine that right now there is no obstacle A, we're just focusing on obstacle B. So link 2 can rotate freely 360 degree within this region, but once it reaches this area where link 1 is in collision, okay, so link 2 automatically will be in collision with B. Okay, so it means that when the angle is between a little bit more than 90 degree and less than 270 degree, so there is collision, and it's for all values of your theta 2. So for this value of theta 1, the link 2 will be in collision for all values from 0 to 360. So that's why we have drawn here a big obstacle in the C space. So this is so actually it looks like something like, if you accurately draw it, it will look like something like something like this. So actually the collision for certain values of theta 1, okay, even if the theta 1 is less than 90, okay, and theta 2 is also somewhere, let's say 90 degree, then there is a chance that it will collide with obstacle B. So also we include this region also, and same is true for after your theta 1 is more than 180 degree, and then there is again a chance that depending upon the value of theta 2, there is a chance that it will collide with the obstacle. So that's how we map the obstacles from the workspace to our C space. And now the mapping for the obstacle A. Obstacle A, as you can see that once the link 1 will, so we'll just name it here. Should I name link 1 here? Link 1, link 2. So when the link 1 is link 1 can actually move like positive, it can increase gradually, and there will be some values of theta 2 that this link will be in the collision with the obstacle, unless you change the angle of your link 2. So if the link 1 is also, let's say, between 0 and 45, and your link 2 value is straight like 0, then there is a chance that it will collide with this obstacle. Okay, so what you need to do, you need to actually move this link 2 little bit backwards, like the angle of maybe 270 degree, and then there is no collision. So you see here in this region there is no collision when theta 2 is more than, actually you can say, you call it more than 90 degree, or between 180 degree. In the range of 180 degree there is no collision, but for the value between roughly around 45 degree there is an collision. So I have made obstacle here, and this obstacle will look like in the C-space something like this. Okay, this is because even if your link 1 has angle 0 and your link 2 has angle like 90 degree, it will still gonna collide with this obstacle. Okay, so imagine here link 1 90 degree and link 1 0 degree and link 2 is 90 degree, so there is a chance of collision here. So this is collision for link 1 0 and link 2 90 degree, and then there is a chance of collision when the other way around, when your link 2 is, let's say, 45 or 90 degree and link 1 is 0, so there is also a chance of collision. So this is one collision obstacle, and similarly the other possible values where the collision can act is the when your theta 1 is low and theta 2 is very high, like in the range of above 270 degrees. So in this range also you will get obstacle, the collision. So I've drawn it here like this. So imagine your link 1 is something like here, this link 1, and then link 1 has small angle here, and link 2 has an angle of 270. This one is actually starts from 360, so link 2 has 360 degree of the angle. So this one we can make them smaller. So this is obstacle A. Okay, so yeah, and so this is obstacle A, obstacle B. Sorry, this is again obstacle A in the C space. You see that one obstacle can be split into multiple obstacles in your C space. So one portion is here, one portion is here, and then there is also one small portion here. This is the, again, when the values of your link to angle or join to angle is very high, okay, like in the range of 360 degree, and your theta 2 is somewhere near the 45 degree or 90 degree, then there is again a chance of collision. So that's what we have written here, and what we can do is to separate it a little bit so it's more visible. Okay, so this is how we do mapping of obstacles from the workspace to your C space. So now this region, the white space region, this is C free. Okay, here this is C free, all the white region here, and this our start point here. So here it will become the start point of this will become here. This is the start point, and when the when the link 1 also have a small angle and link 2 also small angle, so this is our start point here. And what will happen that the robot will, now if we want to do path planning here, so what we can do just by visually seeing that, first I think this theta 2, it should gradually increase, okay, and theta 1 should decrease. So what will happen, this link 1 will move a little bit downward, and this link 2, it will move like this. So the next configuration will be that theta 1 will be a little bit downward, less, and theta 1 will decrease and theta 2 will increase until your this end effector will, should I draw here the end effector too? Let me draw here. So this is your end effector, let's say. So your end effector will reach like the position here. It will have a position like this. It will become complex. So it will, the end effector will move like this here. So it needs to be down from this, below this obstacle, so it can avoid the collision. Otherwise there is no chance to pass this, avoid this obstacle. Okay, and once this, so here how we can draw it, we can draw it by when the angle will, theta 1 will decrease and theta 2 will increase, so it will be like this. Okay, and then it will come from here. Okay, and then it will so here the theta1 will decrease further, and after the obstacle A is gone here, the theta1 will start increasing, like in this direction. Theta1 will start increasing, the robot will start moving further, but you can see that theta2 here, this will also then start increasing step by step. I cannot draw here all the complex steps that they have drawn, but for the, I think in the detail, if you want to go, then just refer to the book Modern Robotics, and the figure is 10.2. There they have drawn the step by step, all the steps here. And so yeah, so it will go from there, and then angle decreasing, and then both angles will start increasing, and then finally from the angle for the somewhere at the angle will be from here, it will, both angles will start increasing again. Till it reaches, so that our end effector will, end position is somewhere here, goal position we can call it. This is goal, this is start position here. Here I'll change the color again. So in the workspace, the robot will move like this here and then reach this configuration, okay? But in the C space, it's all about angles. The angle first, theta1 will decrease, it go down, and theta2 will increase, and then theta1 will keep decreasing, theta2 will keep in from this region, it will also, theta2 will keep increasing. So theta2 is always increasing, okay, as you have noticed here. And yeah, so from then after when the obstacle is almost passed, so what will happen, then theta1 will also start increasing in this region. Theta1 increase and theta2 will also increase till it reaches this configuration, which is the goal configuration, and this is the goal configuration here. So this is how we do the path planning or motion planning of a 2-hour planar robotic arm. And this is how we do mapping from workspace to C space. Without this mapping, it will not work. Okay, you can do path planning only for the end effector, but it will only avoid collision of the end effector, but there is chance that your links will still collide. That's why you have to convert always the workspace into your C space, and there you have to convert the map the obstacles, and then you have to do motion planning. You can use grid methods, you can use sampling based planners, and this will give you the final path. So this will be your path from start, then here, and here, and this path has nothing to do with your actual path. Actually, the robot will be moving like this from this configuration to this configuration. It will first move downward and then start moving there and then reach there. So these two are completely different worlds.